Okay, hi dear students, you're welcome to this lecture, which happens to be part one of electronic structure and the periodic table. And the reason why I call it part one is because to some students it is lecture 3, to some students it's lecture 4, to some students it's lecture 5, depending on the course you're taking. So let's just go into it. So the course, as I said earlier, is electronic structure and the periodic table. So in this lecture, we'll be looking at quantum numbers. I'll explain what it is or what they are, and atomic orbitals, the shapes and sizes, electronic configuration in atoms, orbital diagrams of atoms, then the electronic arrangement of monatomic ions, and then your periodic table, your periodic trends in the properties of atoms, how the trends in the periodic table actually relates to its properties or properties of different atoms. So we'll just get right into it by starting off with the arrangement or arranging electrons in atoms. So we are looking basically at the electron configuration, just as how the electrons are arranged in the atom. Because anytime you think about the word configuration, it's just like a setting, how it's set. So you're looking at how the electron is set or arranged in the atom. So this associates the energy level with the number of electrons in each level. So the way it works is that with every energy level, there is a particular number of electrons at that level. So it relates the two together. So it's an association of those two just to make the settings of the electron in the atom. So I have what we call the atomic diagram or the orbital diagram, sorry. And the orbital diagram just shows the arrangement of the electrons within each level. So you have the electron configuration and you have the diagram that shows arrangement. The first one associates the energy level with the number of electrons on each level. And then we talked about previously the periodic table, and we saw how the electrons how the electron increase successively across, and how it also does that going downwards the periodic table. So the electron configurations of elements can be deduced from the positions on the periodic table because there's a set structure. That's how it moves. So we now move down to the quantum numbers. So there's an individual called Schrödinger, and Schrödinger came up with this equation, and this equation is able to solve approximately for atoms, and it can be solved approximately for atoms and of two or more electrons. So what the equation actually does, it actually predicts where an electron or electrons will be in space at a certain given point in time. So the solution results in orbitals which have an energy and a shape and orientation in space. So the puzzle back then was this thing called an atom. They have electrons, and they several electrons. So how do we find where these electrons are? How do we find what energy level they are at? So he came up with this equation, and this equation helped in solving that problem. And then the solution results are the quantum numbers, and the quantum numbers are what we're going to now take our time to see. So and the word quantum, by the way, is energy, and at every level there's an energy at every level, and hence you're tracking where the electrons are, because when you know where the electrons are, you know the energy level. Take for example your year. As a student, you have your first year, second year, third year, and fourth year, and in every year the potential or the capacity of a student is assessed. A first year student cannot compare himself effectively with a final year student. The capacity of a final year student should be more than that of a first year student, because the first year only has a first year experience and it's almost synonymous to the energy levels. So first year, second year, third year, fourth year, that's kind of like the thing. And we're going to be looking at quantum numbers for the first, second, third, and fourth. So that's a good comparison. So I have the first quantum number, which is denoted N, and it's the principal energy level, and it's specific to the first quantum number, and that's N. And you can have 1, 2, 3, 4, and it goes on and on. So the N equal to 1 is the first principal energy level. Then you have the 2, which is the second, and then it goes like that. As the value of N increases, the energy of the electrons also increases. The same thing. The increase is not just numerical. The increase also causes, it also indicates an energy increase in energy as well. So we have the second quantum number, which is denoted L, and each principal energy level, which is specified by N, has one or more sublevels, and these are specified by the quantum number L. So I'm just, forgive me if I'm going back and forth just reading. I just want you to understand what is meant by what is said there. So notice that you have the first and the second have a relation, and the relation between the first and the second is the fact that the first minus 1 gives you the second. The first minus 1 gives you the second, and in the N principle there are N sublevels. So the N is the first quantum. So and the sublevels now are denoted your S, P, D, and F. So it's either an S, a P, a D, or an F. It can be an S and a P. If it is an S and a P, there's a condition, and that's what we call in chemistry, is called hybridization. But individually you have those sublevels single. So it's the S, which is at the end the S orbital, there's a P orbital, there's a D, and the F. So it's either one of these orbitals. It's not and, it's or. So for the items of the electron, we talked about the energy. So the S is less, the P is greater than the S, then the D is greater than the P and the S, and then the F is the greatest of them all. So you have the 4 of them as indicated there. So we'll see them more graphically by this, where you have your N, which is your first, second, third, and fourth, and then you have your L, which has your zeros and 0 and 1. That is what the L is. So if you look very closely, you see that the S is indicative of 0, because where you have your N being 1, 1 minus 1 is 0, which is your S. And for the 2 is 2 minus 1, which is 1, which is the P. And then for 3 minus 1 is 2, which is the D. And then for the 4 is 4 minus 1, which is 3, and that is indicative of the sublevel denoted F. I hope that makes sense. So it's going to make sense as we go further. So we have the third, and as the first, the relationship, as the first and the second, relationship with the third is the second. Notice that they're all tied together, but the relationships are with their immediate, the close relationship. So with each sublevels contains one or more orbitals, which differ from one another in the value of the third. That's this third now. So you have the first, second relations, then the third now differ in the value of the third, the difference now. So going further now, you see that with the L, whatever value you have for the L, notice that there is now going to be a range in some level. I'll explain how it all ties together. Just follow me slowly and don't miss where we're going with it along the way. Just stick with it. So now for D, and if you remember, the L is 2. So if the L is 2, it means that you can have positive 2, positive 1, 0, negative 1, and negative 2. That's for the D. For the F, since it's 3, since the L or the second quantum number is 3, you can have positive 3, positive 2, positive 1, 0, negative 1, negative 2, and negative 3. So it's almost like you're moving from positive axis to negative axis. That's just technically what it is. So then the fourth quantum number is related to the it's called the MS, related to the electron spin. It's associated with the electron spin, and your spin can be clockwise or anti-clockwise. So it's either a plus half or negative half, which is just indicated with clockwise and anti-clockwise. So notice that it can only go two ways, clockwise, anti-clockwise. Then we now look at some principles, and these principles are there as laws to guide and ensure that there are no mistakes or nothing goes wrong. The reason why we have laws is to instill order, because we're talking about arrangement, talking about structure. So with all of those things, you have order to it. So Pauli's exclusive principle states that no electrons in the same atom may have the same set of 4 quantum numbers. So you cannot have the same set. The same way no student in university should have, no two students should have the same student number. It's going to cause a problem if 2 students have the same student number. So on the basis of that, on the strength of that, you have differences that leads up to that one whole unique identity for a particular electron, and there's a reason for it. So this image just shows us the permissive value of the quantum numbers through n. For just look at the, I don't know whether you can see it very clearly. There's a spatula that was used to pour a compound on water. Notice the difference in intensity of the particle as they go down to the bottom of the beaker. So you have range, so you can have the weak or the lesser energy or lesser force here, the one afterwards, and then the highest will be the ones that take it down here. So just to indicate the whole idea. So now we have an example that we're going to observe to see which is a valid set or a set that doesn't exist. So it's like once you have some set of values, you can be able to tell when the numbers are off. Like if you see a number, like take for example, we're in 2020. If a student shows up with 2022 student number, you can know that that number is off, because the way the system is structured, your student number comes according to year, and if we're not even around or near that year, you can have that number. So kind of like the same idea we're going to use to figure that out. So for the first, we have 3, 1. So just to read the questions, I know you can see it. Consider the following set of quantum numbers in order: N, L, M, L, and MS. Which ones could not occur? Say for valid sets, identify the orbitals involved. That's the question. So we have 3 here, 1, 0, and half. So for the first, 3 is the N, the L is 1, and remember we said the N minus 1 will give us the L, but in this case it could be 2, it could be 1, it could be 0. So hence you have 1 there, which means that it's valid, and then you have the 0, because for the 2 you could have 2, you could have 1, you could have 0, could have -1, sorry, and -2, so that's valid as well. And for the ms, you could have a +half, which is a clockwise, and -half, which is anti-clockwise. So that's very valid, and that's how we'll go on and on to check. So let's just look at the solution straight up. So we have the 3, and then you have your p, which is indicative of your 1. So remember, I said 0 is s, 1 is p, 2 is d, and then 3 is f. So notice that you have a valid, this is valid on the basis of what you have straight up. And for the second, notice that you have 1. And remember, 1 minus p is 0, so you cannot have a 1 for the next. And even a 1p doesn't exist. You only have 1s. If you go back to our table here, so you only have 1s, you don't have a 1p, so hence it becomes invalid. You have 2s, 2p, 3s, 3p, 3d, 4s, 4p, and 4d and 4f. So we see that the second one cannot exist on the strength of N1 and L1. That cannot work. And then you have the second one, the third one, sorry. So you have 2, and then you have 0. The 2 and the 0 here is s, so it's 2s, and then you have a 0, and you have valid. So you have the next one here, have a 4, and then a 3 is indicative of an f, and then you have a 2, which is valid, and then the half. So that's there, valid. Then you have this other one, you have a 2, and then 1 is indicative of p, which is a 2p, is valid. But when you come down to 0, valid. When you come down to the other 0, remember your spin has to be +half or -half, or in this case you have a 0. So on the strength of that, it's not valid. So I hope that makes sense. So we now are looking at the atomic orbitals, shapes, and their sizes. So the orbital is a physical representation of a region in space where there are 90% probability of finding the electron. Remember, as I told us before, Schrödinger's equation is trying to figure out how the probability is basically where you can find this in space. And I joke with the students, I tell them this, I say, do you know that technically you might be sitting in a location or your house can be in a location for years and still not be in that particular location in space? Because think about it, if the world is moving and you are static, you are not necessarily static, you're moving technically, but the world is moving. It's like a car, you are seated in a car, but the car is moving. So will you say you are not moving because you are seated in the car? No. The tool you are in is moving. The vehicle you are in is moving. Hence, you are moving. But if you are seated, and even that, if you think about it on a global scale, the world is in motion. So technically, in space, you had moved, but a very not considerable move to your eyes. So hence, just thinking about that, because even the electrons in space are kind of like our solar system, where you have the sun, which can be seen as the nucleus, which contains a proton and electron, and then you have the other planets revolving around about it. So it's kind of very similar and very comparable, and it's interesting when you think about the large perspective of things, or the large way the universe is, and then come down to the very small thing as atomic, and you see the same system just replicated on both extreme ends. So we say the shape, you have the s orbital, which I say the s, and the s orbital, which differs only in size. So it means that the more, if you have 1s is small, 2s is bigger, 3s is much bigger, like that. And then you have the p orbital, which consists of 2 lobes, which is your axis, and this axis you have 3 of them. So it's 2 lobes, 3 axes, 2 lobes, 3 axes. We'll see it very clearly. So it's the px, py, and pz, almost like your 3-dimension. So this was what we're talking about, the s orbital. So you have the 1s, which is small, 2s, which is a little bit bigger, 3s, which is much more bigger than the 1 and 2s. So it's kind of like your electrons around this orbital will be found in this blob of space, while the electrons in the 2s will be found around this. And don't always assume electrons to be like this. Most times you can have a cloud of electrons. So hence the whole idea. And this is what the lobes will look like. So you have one axis, and then that axis gives you the two, like a positive and negative side. This axis to positive, negative end, so you can have electrons around about that range or around that orbital in space. Because the idea is that where is this electron at this given point in time, you can find it around that lobe in space. So yeah, this is how you like write the order, like the configuration, how you write it down. So it's 1s, and s has 2 electrons max, p has 6 electrons. So you have them like that. So it's s2, p6, and then d has 10, and then f has 14. So that's kind of like the order for them. And once you're writing it down, take for example hydrogen, you just write 1s1 because it can take 2. So for helium's 1s2. So it's kind of like the idea, you keep on going as such. So notice that when it gets bigger, there's a certain order to it. In the class I drew on the board the other format that you can use to get the order, because this is how you consequently be calling it. And notice that it's by rank, it's not just random. 1 is the smallest, 2 is the second in command, and then you get to 3, which is bigger, and then you notice that 4s, because 4s, the s orbital is not as strong as the d orbital, so hence it's pushed down, and it's the only one that follows after the 3p, which is not a 3, it's a 4, and then you have the 3d, 4p, 4d, and 4f. So you have those interjections here, so it's the only one that slots itself in between. If not, others are just 1s2, 2s2, 2p2, 3s, 3p, and then you see the 4s comes in between before the 3d, and then 4p, and then it goes on like that. That's how the energy increases. So in this example, we're asked to find the electron configuration of sulfur and iron atoms. So first and foremost, you need to know what is the number of electrons that sulfur has and iron has, and you can be able to, using what I stated earlier, the electron configuration, the order, then you write it and the number of electrons present, so that it totals up to the number of electrons that you know these atoms to have. So this is what it is. We know sulfur is 16, iron is 26, so it's 10. That's the difference between them. So you now start filling. So 1s, which has to be 2, 2s, which has to be 2, 2p, which has to be 6. When you total up, that's 10 already, so you need 6. So 3s, which is 2, and 3p, which is 4. You have gotten your 16. So you do for iron, you just continue on. So instead of 3p being 4, you add the total number is 6, and then you have 4s instead of 3d. You have 4s2 and then 3d6. So this is how you write or draw the electron configuration. So the electron configuration from sub-level energies. So once you have once the order of the filling of the sub-level is known, the configuration is already obtained. So once you know what the filling is, you know that S takes only 2, P takes 6, so and you know the number, then you're good to go. You just write it out and ensure it matches the number. So the sub-level another filling before the next level, and so you fill the sub-levels first before you move to the next. So you do that in succession. You don't go fill them one, but there are exceptions to this rule and we'll see them ahead. So this is boron, this is carbon, this is nitrogen. Notice the increment as it goes. So it's 1s2, 2s2, 2p1 or 2 or 3. So there are transition metals too as well, because they all are part of the periodic table. So you have an example here of argon, and it's 18. So you see it goes up on to 18. The first 3 10, the last 2 is 2 and 6, which is total up to 18. And then you have the calcium too. You see the first 10, and then you have 18, 19, 20. So remember the noble gases, those ones are either your 2 for helium and your 6, and your other, because you have all of these orbitals tend to reflect or show themselves in the periodic table. So you have the S, be the group 1 and group 2, the ones that finish out. I'm going ahead of myself, but I'll explain that better when we get to that part. So you have zinc, that's a transition metal. Notice that its D block is full as a transition metal. So that's for zinc, because it's 30. Then you have your transition metals that also have field P. Transition metals that have field P. I think krypton should be a noble gas because of the field P orbital. But you have a situation because of the transition, because it's in the transition element. It's part of the transition because it has the D block also. Or basically, it's a noble gas. So we have abbreviation system by which you can quickly name, because you might in some cases not write the whole 1s2, 2s2, 2p6 to indicate neon. So for short, you just put neon in bracket and then write the continuity sequence. So you do that and then you get your value. And then you have nickel here, which is 28. Do the same thing with argon, and then you have the other part added to it to total up to the 28. So filling the sublevel and the periodic table. So by using the periodic table, it's possible to quickly write down the electronic configuration of elements, so you can tell very easily, and you can assess from the periodic table and see patterns. So take for example group 1s. All of the group 1s will end with S1. All of the group 1s, S1, S1, S1. Think of sodium, S1. think of potassium. S1 just keeps going on like that. And then the group 2 is S2. Group 2 is S2. Even the p orbitals, notice that after the transition from I think the first one should be boron going down like that. That's group 13 to the 18. All of them. I notice that 13 to 18 is 6. 13, 14, 15, 16, 17, 18. So notice that all of them is 6, and it will always wind up to the last 6. So just to make the example clearer, see the group 1: lithium, sodium, potassium, rubidium, cesium. You have all of this: beryllium, magnesium, calcium, selenium, I think, yeah, and then you have barium. So notice all of the different things you said, and this is the abbreviations. These are the abbreviations for different level. So what you see in the abbreviation is the closest noble gas to themselves. So just to continue in the periodic table, you have the elements in group 1 and group 2 filled an S sublevel, and then you have those of 13 to 18 that fill a P sublevel orbital, and then you have your transition metals, that's the D block, and they have sets of 14 electrons. Then you have your F orbital, that's the one that does 14, and those ones are where the lanthanide and arsenide series are present. Notice that in the periodic table that I showed you previously, there was no lanthanide series. They are underneath the periodic table. So I think they're here. Yeah, this is. Let me just go back. So the exceptions to the whole naming or numbering or placing of electron things according to the successive order, the exceptions are chromium and copper. Chromium and copper, because this one either have half full or nearly full, almost half full or almost nearly full. So in that case, it tends to acquire stability, some form of stability, by shifting one of the S orbital electron to the D. Remember, I talked about the energy that these electrons have and how they're mobile. So hence they tend to get excited and move up, so that the D block is either half full, half full or fully full. So the energy levels on this gain stability by position, they have failed, or the field shell. So just to explain what I said earlier, notice that the group 1 and group 2 are holding this part of the periodic table, and the D orbital, this is S orbital, and D orbitals are holding all of this, and notice there are 10, and then the P orbital is holding this whole part down, yeah, 6, and then that's the line and light, they are holding this whole part here, and they are 14. So look here, the orbital diagrams of atom, and how we write these diagrams is by using parentheses. And the parentheses, we have arrows pointing up and down, which indicates the spin in a positive and a negative direction. And I don't know whether you have realized by now that the configuration or explanation of all these things comes down to the split, or comes down to what the electron is, or what the electron is spinning, either to positive, negative. So hence you can never have repeating values. Even if it repeats in the first 3, when it gets down to this, you have to choose either clockwise or anti-clockwise, which makes it very impossible to get mix-ups, except if there was a mistake. So you have the Horn's rule, And the Hundred states that when several orbitals where several orbitals of equal energy are available, electrons enter singly with parallel spin. So hence when you have same energy level, what would then happen is that the spin will be parallel, meaning that one will be going in the positive direction and the other one will be in negative direction. They will not move in the same direction. They can be parallel, which is opposite each other, but they can move in the same direction. Two of them kind of positive, or two of them kind of be negative. One has to be positive and one has to be negative. So this is a long example of boron, and you can see it's 1s2, 2s2, 2p3. So 1s2, you have that. Sorry, 2p1, not 2p3. You have 1s2, so you have this 2s2. So this is 2s2, 2s2, and this is 2p1. So notice that is already done for boron. For carbon, you add one more, and look very closely. Carbon is tetravalent, means that it needs 4 electrons to complete a bond, or to be covalently bonded to for it to be stable. Notice that if you count how many electrons should enter these boxes to complete it, you'll see that it's 4. So how you do it is that this one has an electron, this one has an electron, you have to give this one an electron as well. Then you now come back and give the second one, give the second one, and give the second one. Notice that if you've done the counting, you have 1, 2, and 3, 4. Hence, that explains clearly the tetravalency of carbon and so many other things as well, and the structure and the nature of it as well. So you have for nitrogen, which just needs 3. You have for oxygen, which just needs 2. And you have for fluorine, which just needs 1. And you have for neon, which is full and it's not needing anything. So note that on the basis of the parallel nature of these electrons, there are certain properties that can arise. When an electron doesn't have when it's unpaired, it can have a property of paramagnetism. If it's paired, it can have a property of dimagnetism. So all of these magnetic properties, varying magnetic properties, can happen as a result of a parallel situation or just a single situation as well, unpaired or being paired. So that's that. So we'll look at this example and then we'll continue in the next. We'll look at this example very quickly before we end and then continue the other part. So construct an orbital diagram of atoms of sulfur and iron. Remember we did sulfur and iron previously, so we know their values. We know sulfur is 16 and iron is 26. So one of the important things is that how we know the number of the orbitals, the pairs, because we saw that with boxes, and we know which one we need or which one needs what is on the strength of a given value. So, and this is how to apply on Hund's rule. The electrons enter singly in the parallel spin when several electrons are equal to the individual. So that's what I demonstrated when you said you have several electrons, you have 3 boxes, you have to fill the 3 and not stone all the 2 electrons in one box or 3 electrons in one box. You have to share them equally. That's justice. So Here we now see for sulfur. So it's 1s2, 2s2, 2p6, 3s2, 3p4. So how we know the number of orbitals, that's that parenthesis, how we know the numbers to make is from this formula where you multiply the value for L by 2 and add 1. This is what is explained here, multiplying the value for 2 and then adding 1. So that's gives you that this is 1, P is 1, multiplied by 1 plus 1 is 3. Then for D, it's 2 multiplied by 2, which is 4 plus 1 is 5. And then 3 multiplied by 2 plus 1 is 7. Hence it's 14. That's how we get the values for what I told you previously about the orbitals, or the amount of electrons that can be contained in orbitals. So you have this situation here as 1s2, and you can see the 2 here, 2s2, and you can see the 2 electrons here, and then 2p6, you can see them here, 3s2, you can see them here, and 3p. Notice that the 3p, because it's 4, you fill 1, 2, 3, and then the fourth one you take it here. If there comes an electron to be here and here, and that's it. So that's for that. And then we see for iron. So since iron has a D block, we'll then have to do the D, which is 2 times 2 plus 1 is 5. So we have all of those details, then we'll start filling. So in this case, you have 1s2, 2 electrons, 2s2, 2 electrons, 3p6, you have 1, 2, 3, 4, 5, 6, and then 3s, you have the 2 electrons, 3p6, you have 1, 2, 3, 4, 5, 6, and then the 4s, remember we said you don't do 3d, you do 4s, is 1 and 2, and then the 5, and the 3d is 6. So you have 1, 2, 3, 4, 5, and then the sixth one will come back to 1. So we're going to continue, we're going to stop here and then continue the other part in the next video. So we'll see you in the next video. In the next video, we're going to talk about electron arrangement in monoatomic ions. So do well to study this part, understand it, try some exercises without seeing the solutions, and then just get acquainted with it as you prepare for an exam that is around the corner, or quiz that's around the corner. Thank you and bye for now.